took a year's postdoctoral fellowship, a NATO postdoctoral fellow at Munich, Germany, where he extended these kinetic jump, temperature jump studies under Professor Heinz Gerischer. I couldn't find where I phoneticized it. He spent 3 years then as a research chemist at the Naval Warfare Center at China Lake, California, before coming to Murfreesboro and being a professor here for about 9 years. He was here 1969 to 1978. As a matter of fact, he left just months before I arrived. And I've always wondered if I should take this personally. But even while he was here, he spent the summers at the Naval Warfare Center or Brookhaven National Laboratory. He returned to China Lake in the chemistry division in 1978 and stayed there until recently, with the exception of the year that he worked in the New Hydrogen Energy Laboratory in Japan. He returned this fall as a visiting professor. He's also a candidate for our physical chemistry position. Dr. Miles has published nearly 200 papers in the general areas of electrochemistry, thermodynamics, and energy conversion. And these have been especially applied to lithium batteries, supercapacitors, molten salt systems, and palladium-deuterium systems. And he will talk today about his interest in that area in a seminar titled 12 Years of Cold Fusion Research, Excess Enthalpy, and Helium Short Bursts.
Okay, thank you for that introduction. One thing I want to point out is that a lot of this work was performed at the Naval Air Warfare Center. We were funded by the Office of Naval Research to work on this in about 1989 to 1995. Actually, a lot of people don't realize this, but Office of Naval Research funded Fleischmann and Pons before they ever made the announcement. They were funding this work before anybody knew this work was going on. The work at China Lake on this area discontinued in 1995. I went to Japan and worked on actually about 6 months in the winter. Had a lot of snow there. It was 1997, 1998 winter period. Just give a little background on the cold fusion area. Of course, it started with that infamous announcement, premature announcement by Martin Fleischmann and Pons, March 23rd, 1989. They did not want to make that announcement, but Steve Jones of BYU was claiming he had similar results and he was going to publish his results. So they were forced, the university got forced him to come out and announce their results prior to that, because of the possible patent problems and so on. But it was premature and should not have been done at that time, obviously. It created quite a stir. It was on the news media. Time magazine had a cover story and so on. And the Department of Energy got involved and investigated what was going on and published a report in the fall, very quickly after this, in the fall of 1989. The DOE report came out with pretty negative. I'm actually in that report as one of the groups seeing no excess heat, because I never saw anything for 5 or 6 months. I was getting the heat I put in was equal to the heat I put out. So I was in that report on the other side. Some people refer to people in this field as believers or non-believers, like it's a religion, but I guess I was a non-believer back then because I was on the other side of the fence, as far as that goes. The first international conference was held in Salt Lake City. By then I had found excess heat. The result depends on the palladium, it depends on the material, and I tried other palladium and I finally got excess heat effect later on, and we had a conference there, the news media was there, and this was my first experience of making big science. Hot fusion people were at that meeting, and as soon as the person had sat down, given a talk, they would run to the microphone and they would ridicule. My first experience with scientific ridicule. They would say, this sounds like something out of Alice in Wonderland, and I've never seen that at a scientific meeting. The news media, of course, ate it up, and the field got off to a bad start. This was mostly hot fusion people that did this. I've since learned that the hot fusion community, I've heard comments that they had a policy because they needed this funding for hot fusion. But when something new came out, their policy was to either smash it or grab it. And cold fusion was something that had to be smashed to protect their funding. And so I think this is basically what happened to the field, in my opinion. It's not helped by the fact that the effect is very difficult to reproduce, so that made it very difficult to prove the effect as well. From there on, we sort of continued in quiet. We had a quiet meeting in Como, Italy, the second international conference. At that meeting, I reported that the XSC correlated with the helium 4. These all critics were saying, well, if it's fusion versus fusion product, well, the fusion product is helium 4. And of course, that's hard to convince people because helium 4 exists in the atmosphere at 5.2 parts per million. And so the field more or less went underground, and we kept having international meetings. I'll skip a lot of the international meetings, but the last one was in Italy in May 2000. There's a book, A Conference Proceedings, published on that meeting. It's published by the Italian Physical Society. There's a lot of excellent papers in here. In fact, so many papers I haven't even read them all. So there's certainly a lot of work going on around the world, different areas, but we're not being allowed to publish in scientific journals, so it mostly appears in books like this, the conference proceedings of the meeting in Italy in the year 2000. There is a section on cold fusion at the American Physical Society coming up in March next month. We have a case from MTSU related to that we're presenting based on the work I did since I arrived here. Of course, I don't think that society likes us having these meetings, but they can't stop us because the member is sponsoring them. So our session is on Friday after everybody's left, pretty well. but in May also we have the 9th International Conference in China. These conferences alternate between Asia, North America, and Europe. They go through a rotation, and so they rotate between those three continents. Just to point out, this is from the DOE report, that report that more or less squashed cold fusion. In fact, the head of that DOE group was Huizinga, last name Huizinga. He later wrote a book called Cold Fusion, the Scientific Fiasco of the Century. So I don't think he was very open-minded to this to start with. But this just shows you, you can get this on, you go to the internet and just go to DOE, Department of Energy, and put in cold fusion report. This will come up. And I just printed this out the other day. But the group not conserving excess heat, you have MIT and you have Caltech and you have my work at the Naval Weapons Center, not conserving excess heat. So I'm on the other side in that report. The palladium-deuterium system, we now know that we only get excess heat when you get a high loading, at least a 0.8. So 80%, 8 atoms out of 10 have to. For every 10 atoms of palladium, you need 8 atoms of deuterium, for example. You try to get loading up to 1. It's even more excess heat when you do that usually. Martin Fleischmann believes condensed matter requires quantum electrodynamics for explanation. You have a condensed matter here. You have a high concentration. You put this as molar concentration. Palladium and deuterium are 110 molar. Electrons are 5,170 molar. So you've got a lot of things interacting. And to treat that, you can't do that too well by quantum mechanics. You need quantum field theory or quantum electrodynamics to treat this. The deuterium actually goes into the palladium as a positive ion. Once it gets in there, it gives this electron up to the palladium, and it's a positive ion. It doesn't have any electrons, and it diffuses. It will migrate. You have electromigration. If you pass the current along the wire, it will migrate towards the negative end of the wire. And also unusual is the deuterium ion has the highest diffusion coefficient. You'd expect it to be hydrogen, deuterium, and tritium. You have a reverse order. Deuterium has the highest diffusion coefficient, and deuterium is a boson, and the other things are fermions. That might be an explanation perhaps. These are just some biographs of Martin Fleischmann at the last meeting in Italy. He went into cold fusion because he was looking for the electrochemical experiments that you could not explain unless you used the quantum electrodynamic approach to explain the result. And he thought of different things to do, but this is what he chose to do, the energy, the link nuclear process, and so this is why he even went into the field, was because of his interest of finding things that had to be explained by quantum electrodynamics, which could not be explained otherwise by quantum mechanics. And this was his hidden agenda then, was to investigate systems that when you study their properties, what you found experimentally required a QED explanation. And that was his hidden agenda why he went into this area. He stated that if he did not think things could act together in a condensed matter system like this in a coherent way, he would not have ever tried the experiment. Because he thought all these things in condensed matter could interact, which is explained by quantum electrodynamics, that effects would be possible. Martin Fleischmann's interest in quantum electrodynamics led him to meet up with Preparata in Italy, and Preparata later wrote a book, QED, Coherence and Matter, which covers a lot of different topics. With Chapter 8, he presents a theory of cold-fusion based on quantum electrodynamics. And in this he states that you need a high deuterium loading according to his theory, which is what we found experimentally. He states that his theory predicts helium-4 as the main product, which is what I found experimentally, and other people as well by now. And you could actually get high excess power densities up to over a kilowatt per cubic centimeter. Now, I've never seen anything that high. I usually get around 1 watt per cubic centimeter, but some people have reported energies, excess heat that high as kilowatts per cubic centimeter of plate. But personally, I have not seen the results that large. Now, the Navy was interested in this from the beginning. As I said, they funded Fleischmann and Pons before it was ever announced. They continued to look at that after the announcement, and we had a 3-laboratory program going on: Naval Research Laboratory, Washington, D.C., my group at Lake, California, and a group also at the Space Naval Warfare Center in San Diego. Our names have changed over the years. Naval Research Laboratory is the premier Navy laboratory, and their name has stayed constant. But we've gone through a few name changes over the years. The main result of Naval Research Laboratory is they were to make the materials. We knew it was a material problem. We wanted our own in-house materials. And for almost 2 years, they made materials and sent them to me, and I studied them, and they never produced excess heat. Very frustrating. You spend a year or two and never seen any effect. It was only towards the end of this program that they made a palladium-boron material, and that has produced excess heat nearly every time. I'll talk about why maybe a little later. Our main result, we found excess heat in some experiments, and the excess heat correlates with helium-4 being produced when we see excess heat. The San Diego laboratory developed a different method, co-deposition, where you deposit palladium out of solution onto a copper cathode at the same time it's loaded with deuterium, and it shows excess heat fairly quickly and quite reproducibly. And that work is still going on, funded mainly by a person in San Diego. He's been cited several times for waste, fraud, and abuse because he continues to support that work in San Diego. That work is still going on, co-deposition method with Stan Spock and Pam Voss in San Diego. The work I did in Japan on the palladium-boron was published as a naval research report, about 155 pages. I have a copy of it here. Martin Fleischmann is the main author of this. I brought the data back from Japan. It was a computer data acquisition, a data point every 5 minutes for about 70 days, a lot of data. And he did a thorough analysis of this data, and we wrote this up as a Naval report. Dr. Imam of Naval Research Laboratory, but most of the work in here is done by Martin Fleischmann. Dr. Imam is the one to contact if you want a copy of this report. This is a supplemental number and email address. This came out in March 26th of this year, this report. It has almost everything you want to know about that particular system, analysis by Martin Fleischmann. Incidentally, when the the director of the Naval Research Laboratory, Dr. Tim Coffey, found out that we were about ready to publish this. He tried to block it because, not everybody in the Navy agrees with us. And he tried to block this publication. It was already going to the printers, and everybody had approved it, but when the head of Naval Research Laboratory found about it, he did not want to publish under NRL names. And we had to appeal to the head of Office of Naval Research, Dr. Fred Saltfield, who had funded some of this work, and he recommended publication, and so Tim Coffey had to go along with that because he was the boss over at the Naval Research Laboratory. But you're always running into these problems. Even though we're doing this work in the Navy, not everybody in the Navy agrees. We have a lot of critics in the Navy as well. Now, we believe the major reaction in the cold fusion, both in Preparata's theory and what I found is the deuterium fusion to form helium-4, and the energy is given off to the metal lattice 23.8 MeV of energy. That's a tremendous amount of energy when you think about it. 1 cubic centimeter of palladium-deuterium, just 1 cubic centimeter, would produce this many joules, 1.3 times 10 to the 11th joules. That's the calculation if you wanted to go through it on the bottom. That's equivalent to the energy of 32 tons of TNT. Now, this could cause a lot of concern. 1 cubic centimeter, if you could cause it to all be released suddenly, 32 tons of TNT. In light of what happened in New York City on September 11th, that is certainly a concern. I've tried to alert the Navy to that. I don't know what's going on exactly, and it may already be known. Part of the problem with cold fusion, maybe this was already known, and maybe it's already a black program, as far as I know. But it certainly is a matter of concern. And you could also express it as you get 1 watt for 4,000 years, or you could get $3,610 worth of electricity at 10 cents a kilowatt hour for that much energy. So that's certainly a lot of energy. We just barely tickle a little bit, just get a very tiny part of that out in the reactions I've seen, of what actually could be obtained. The hot fusion reactions, you form an excited helium-4. You don't have any nearest neighbors, it's plasma, and this can break up either with 2 protons and neutrons to form helium-3, and the neutron, or it can form a tritium and a proton, and these are about 50-50 in the hot fusion pathway. This is much smaller, about 10 to the minus 7. Very, very rare, this reaction here. Where you get a gamma, high energy gamma produced, a 23.8 MeV gamma, which would carry the energy quickly out of the cell, probably out of your building and into the next building, where that would, energy would be deposited, that high energy gamma. So that's not what we see. The energy is winds up in the cell. Of course, one argument was if you're generating 1 watt of excess heat, you should be getting 10 to the 11th neutrons per second, and that would be deadly. And so a lot of the argument the critics made, if this is really true, where are the dead graduate students? Why aren't they dead? Because the ones that worked with Martin Fleischmann should have been killed. If they were getting this reaction, and getting 1 watt, they would not have survived. So that was one argument of the critics. But the pathway in a condensed system like palladium-deuterium is not these pathways. It's a different pathway, and the energy is given up into the metal lattice. Now, our first study of excess heat and helium, we collected gas samples in a glass flask. We did not have the capability to measure helium-4 at China Lake, so I shipped these to the University of Texas in collaboration with Ben Bush, who was there, and we found that we could only get orders of magnitude levels of helium-4 measurements, but when we had excess heat, we had elevated levels of helium-4. And if you order of magnitude, these are around 10 to 11, 10 to 10, 10 to 12 helium atoms per second per watt. This reaction theoretically produces 2.6 times 10 to 11 helium atoms per second per watt. So we're within order of magnitude, we're between 10 to 10 and 10 to 12. And when we ran control studies, we did not see any helium. We could not detect any helium. Even this experiment is at the lowest excess power, if any. It might have been experimental error. We could not see any helium-4. So we were getting, when we had excess heat, we were finding helium in the flask, when we were not getting excess heat or when H2O controls, we did not find helium-4 present. Of course, the argument of critics were that the helium was diffusing through the glass, but why would it diffuse through in some cases, not in others? And why did it diffuse into the glass only when we had excess heat and not the other cases? It was hard to reproduce excess heat. Like I said, we'd go a year sometimes without seeing the effect again because we didn't know what materials would work, which I do understand a lot better today. But we saw excess heat again in the 1991, 1992, not as large, it was rather small. We're getting better at calorimetry, so I think this is correct. We reported the results to a third party. We reported our helium-4 results to a third party, and Rockwell International measured the helium-4. Brian Oliver's the world expert, and he reported his helium-4 results to third party, so I didn't know what he got, he didn't know what I got, and it was later I got the results together, and he measured helium very accurately. This was his 1 sigma. So from here to here, that's an 8 sigma. From here to here, that's 37 sigma. That's his error limit that he gave. And after I corrected for the background, which I later found we had some background present all the time that got into the system, then I calculated results of 2 times 10 to the 11, 2 times 10 to the 11, 5 times 10 to the 11 helium atoms per second per watt, which is pretty close to what the theoretical value is of 2.6 times 10 to the 11 helium atoms per second per watt. To continue to answer critics, we went to metal flasks because helium does diffuse through glass. That is a true statement. It's slow enough that I calculated it would take 28 days for enough helium in the atmosphere to diffuse through the glass to equal my background level. It would take me 28 days. It does diffuse through glass. There's no question about that. So we went to collecting the gases in a metal flask where there's no question about it. Helium does not diffuse in metal flasks. This is a series of studies, and these when we got excess heat, we got excess helium, and when you calculate helium atoms per second per watt, you get in the order of 10 to the 11, pretty close to 10 to the 11. Not quite 2.6 times 10 to the 11, but still around 10 to the 11 helium atoms per second per watt for when we had excess heat present and collected the gas samples. This was measured by a third laboratory now, Helium Field Operations in Amarillo, Texas, which is expert also in measuring helium-4. That's the helium capital of the world, they claim, in Amarillo, Texas. And they do helium measurements all the time. And they can measure quite accurately in parts per billion the helium content of the flask by sensing.
Can I ask a question? I'm misunderstanding something.
Right.
Previous transparency, the background is 5.1 times 10 to the 13.
Right.
So why would numbers in your table that you measure be less than that number?
Because I've already subtracted this from these results.
Oh,
these are already been corrected. I've already done the subtraction. Sorry, in that case, right. So this is what left after I've done the subtraction. And then this is what you calculate. Then you just need to divide this by the number, the seconds it takes to generate 500 milliliters of gases, and divide by the power, and you have this result here. So this is a pretty simple calculation. I think this is around 4,500 seconds, and then we divide by the seconds, you divide by the power, and so that's a pretty simple calculation you get there. But we don't get the full amount. Usually we're low. We don't get as much helium as predicted. We're usually on the low side. And this is the graph that shows this. This is the helium atoms per second. The red line is theoretically what you'd expect, getting 23.8 MeV out of the reaction. That is where you'd expect the points to fall. Most of the points are less than that. I'd have to slide the points this way to higher helium levels to make it equal to the line. And so we are getting less than predicted. And of course, the helium could stay in the metal to some degree. It could be sequestered somewhere else in the cell. And so I don't really expect to get the full amount, but I would expect to do a little bit on the negative side, actually. So it's not too surprising. Other people have found the same thing. They do get helium-4, but they don't get the full amount. Other people in more studies in the last few years, SRI, Dr. McCoubrey has found similar results. He does get helium-4, but he doesn't get the full amount. So to summarize the helium-4 measurements, the experiments where we had excess heat and found excess helium, there were 18. Experiments where we measured excess heat with no excess helium, otherwise the experiment didn't work out as we thought it would, there were 3. 3 cases where we got a result that didn't correspond. I can sort of explain these because 2 used a different cast of palladium-cerium. Now perhaps palladium-cerium doesn't allow the helium to diffuse out. I don't know. That's a possibility. It's a different material. And so 2 of those were with these different materials. The third one was a low D12 level. When the water level gets low and lower than what you thought it was, you can have a calorimetric error. Plus you can expose the palladium and the other electrodes to the gases in the gas. They can start to, they'll be above the solution level gets too low, and you may get recombination of the gases on those surfaces once they're exposed to the gas phase. So I can also sort of rationalize that other one that did not give the right result. Experiments with no excess heat and no excess helium, we had 12. Some controls in water and other experiments in heavy water that did not produce excess heat. 12 times we had no excess heat and found no helium. Experiments with no excess heat and excess helium, which you wouldn't want that we had 0. 0 turned out that way. So we got the right result 30 out of 33 times. And so if you consider that similar to flipping a coin and getting the right result 30 out of 33 times, if you called the coin flip ahead of time and were right 30 out of 33 times, the probability of that is 1 in a million. So that's why I'm quite convinced about these results. Even though the excess power is low, the helium amounts are not high, to get the right result 30 out of 33 times is very unlikely due to error. And then you can top that off with the helium-4 production rate is always in the right range. So how can you also wind up with it in the right range as well as having this probability? So I say the probability is extremely small that this could have been done could have been due to random error. So this is the most convincing result to me, is that the excess heat does correlate with excess helium. And since this was reported, other people have found other results that support the same conclusion. Did you have a question?
Yeah. Do you want to say something about the differences in the experiments? I mean, it wasn't physically different experiments with different materials, for example, or different additions, or is it just the number of times?
A lot of these are totally different experiments using different materials. Now sometimes when we had excess heat, we would collect a gas sample and send it off, and then a few weeks later we'd collect another gas sample. And so sometimes some of these were the same experiment, but quite a few of the experiments were different, using different materials. Some used glass flasks to collect the gases, some used metal flasks. And so these are all over a period of about three year time frame. And so a lot of experiments were totally different experiments that were involved here.
Dr. Miles?
Yeah.
I have a question. I'm a little fuzzy on experiments with no excess heat and no excess helium. Could you describe some of these as to their nature and control and why you would include those as being successful predictions in the final calculation?
Well, of course, one thing you had is we had to set up right early was when we're finding helium, we'd have to establish that in control studies, like in regular water, where we do not get excess heat, that if we do everything else the same, we do not get excess heat. So some of these were experiments in regular water instead of heavy water, and experimentally we got no excess heat. We did everything the same, sent the samples out for analysis, and they found no helium above the background level. So a lot of the controls consist of water experiments. Other experiments we didn't. There are a lot of experiments we set up that never produced excess heat. And so we go ahead and still collect gas samples like we did before and send them off, even though there's no excess heat produced throughout the entire experiment. They never produced excess heat once through the entire experiment, but we send those off as controls. And so those are another kind of control. It's heavy water experiments that never did produce excess heat throughout the experiment.
Okay, but the second part of my question is, why are you including
Well,
Actually, didn't you? Well, it's 30 and then plus 3, so.
well, I guess I don't quite understand exactly
Well,
what
you
you're
have
saying.
18 successful experiments and 12 successful controls.
Right,
That reflected in your statistical probability down at the bottom, 30 out of 33.
right.
My question is, why are you including your controls, which are fundamentally meant to measure what happens at a baseline level, what your 0 point is? Why are you including that in your statistical probability calculation?
Because you need to do experiments the same way to make sure you're not getting helium diffusing in through the atmosphere. And so that serves as the control.
Oh, so these 12 controls were just to test the diffusion of helium through the equipment.
Yeah, to make sure that when you don't get excess heat and everything else is done the same way, you're not getting contamination from the atmosphere into the system. And you'd have to do that to get a paper published, because the immediate question anybody would bring up is, you're getting helium-4, but helium-4 is in the atmosphere, it's diffusing into your system, and therefore so off. And so you have to prove that you can keep helium out when you don't have excess heat. You have to establish that as well in order to make this valid. Now, going into a little bit more detail of experiments of excess heat, this is a work I did in Japan. It was published in Journal of Analytical Chemistry, February 29th of this year, 2000, in Journal. At this point, I can't we don't have this anymore, but I just like to cut some journals to cut, and unfortunately, that's one of them. But this is so I'm going to go into a little bit on the results published in that paper. This is the experimental design of the cell I use, the calorimetric cell. This is the palladium, the rod in the middle, the counterelectrode with the platinum spiral around it. This is the diesel level up here. This holds about 18 cubic centimeters, so it's not a very big cell. I packed this outer compartment with aluminum foil. The thermistors actually sit outside the cell in the aluminum foil area at 2 different positions, one lower, one higher. And then this is in a water bath, and the heat is transferred from the hotter cell here to the bath by conduction. And so this is simply the first law in terms of power. The power in the calorimeter equals the power you put in, which is electrochemical power, plus excess power, any excess power, if any, minus the power that goes out by conduction to the water bath, and the power carried away by the gases. This is open cell, the B2 gas, O2 gas, D2O vapor, all escape from the cell, so they have to be accounted for. So simply heat in, heat out, first law. That's what this equation is that we use. And this is the basic design of the cell. Now this is actually from the publication, and there's quite a lot of things on here, so let me explain. We have 6 thermistors. One measures the bath temperature. The bath is controlled. This is for the bath temperature scale up here. So the bath is very, very constant, within 100th of a degree actually throughout the experiment. We also measure the room temperature. This is a special room in Japan in the laboratory that is pretty well constant temperature. But the main thing is that we have, this is the 2 thermistors in one cell. This cell never produced excess heat at all throughout this experiment. In a previous experiment using the single electrode at China Lake, never produced excess heat. That's why I took it to Japan as a control. It never did produce excess heat in Japan or China Lake. This produced excess heat previously in China Lake. I took it to Japan and produced excess heat again. Now, how do you establish this? Simply, these are 2 thermistors. As you electrolyze the solution away, the level falls, the LiOD electrolyte gets more and more concentrated, and so the voltage goes down with time, so the power you're putting in goes down with time. Therefore, you expect the temperature to decrease with time, and this is exactly what happens in this case. The temperature is going down. This is the temperature scale. This is a scan from the actual experimental data, so this is the temperature of the cell right here. and the temperature is going down with time. This is a chart feeding out from the chart recorder, and so this is time going along this way. And so this is actually how you sort of look at the chart paper right in front of you. That's a little different way to do the scale. So this is a scan of the actual experimental data. And the temperature for that cell goes down with time exactly as you predict. The power is going down with time, the temperature goes down with time. The other cell, we'd expect it to go down with about the same slope, something like that, but it doesn't. The temperature actually goes up with time. Even though the power is going down, the temperature is going up. And there's no way you can explain that except there is an excess heat effect in the cell. How can the temperature of the cell go down when the power you're putting in is decreasing? Unless there's an excess power effect. So this is the simplest way to show the excess power. This is actually about 50 milliwatts, not a lot, but 50 milliwatts of excess power would account for that. Right here we changed the current. We increased the current from 0.25 amps to 0.30 amps. So there's a temperature change right here. Here we had to make up heavy water, so the temperature goes down when you're putting 5 cc's of heavy water in with 18 cubic centimeters. That dilutes the solution and the temperature drops rapidly, and then it starts to come back up. It comes up to a higher temperature because you now again have a dilute solution and you have a higher cell voltage, so it comes up again to a higher temperature. But the fourth point, how can the temperature go up when the power you're putting in goes down? That you cannot account for that except for excess power effect. Notice that two thermistors almost record exactly the same blips here and here. Even though they're in different positions in the cell, some people argue about mixing, but two different thermistors, two different positions, record exactly the same blips. And these blips are due to gas bubbles that go up on the electrode, cause the voltage to go up temporarily for a few minutes, and the gas bubble disengages, the voltage falls back down. And you can see these blips with the temperature. The rise and fall of the voltage and the rise and fall of the temperature corresponds to the gas bubbles building up and disengaging. Roy?
I don't understand why these experiments end. Why is it if you're getting excess heat, you can't leave it alone and keep on getting it? What's the limiting thing that keeps you from going on?
I've run it for several months. Often limiting things is something like Christmas comes along. I mean, you finally get tired of running an experiment, the same experiment.
But I mean, if it's getting hotter and hotter, the temperature goes up, and you leave it a long enough time, how much time have we got here?
Well, eventually you're going to electrolyze too much of the heavy waterway, and so you're going to have problems with calorimetry. Your solution level is going to get very, very low. You're going to start exposing the electrodes.
So the amount of reagents is the
Yeah.
thing that's going to get.
So yeah, you have to add heavy water to make up what you electrolyze away. You have to periodically do that.
Okay, then if you take this same cell and start all over again with the same material, the same electrodes and everything,
Right.
do you get the same thing again, or does it fail the next time?
Almost every time I've got excess heat in one experiment, if I take the same electrode and set it up again, I get excess heat again in the next experiment.
So a given set of electrodes that works, always works.
They seem to always work repeatedly in different experiments. That's true. I found that they're not used up. They will work again in a new experiment.
Then it seems what needs to be done is to design an experiment that keeps running, that replaces the E2O or whatever it is you're using, that will demonstrate this as a continuous thing.
Yeah. Yeah, some people are doing closed cells where they have a recombiner in there where the gases that go up and they recombine with the catalyst and the gases reform the D12, and so you never use up the heavy water. And so the microcurved SRI is done closed cell systems, and some people prefer that method. But it's dangerous because if something goes wrong and that explodes, if you have gases in there, actually there was a person killed at SRI because the cell blew up. And McCurvey even got injured, but another lab person got killed. And I did not like to work with that danger, so I used open cells and did not recombine. But some people do recombine, and then they can just keep on going. That's true. These are just more results, similar results in the same cells. This this cell that never produces excess heat. The temperature always goes down with time. The blips are reproduced by either thermistor. The one that did produce excess heat at the end, you would expect the same downward slope. And if you move it over here, you see there's a departure. And I can calculate this out theoretically. I would expect a negative slope, but I don't get it. And the only way to explain it again is the excess heat effect goes in and the temperature goes up. And so we saw this in many, many different days of the experiment.
What's the change of slope there in the middle? How it kind of comes back? What's that?
Right here,
Yes.
this is where the excess heat is increasing. When the excess heat is increasing, the temperature will keep increasing.
Right.
But eventually the excess heat probably stays constant. As soon as it starts staying constant, then you start the downward slope again. But whenever it's increasing, you'll see an increasing temperature. Even if the excess heat is still there, and it just stays constant, you'll start to see the downward slope again. On the previous experiment, it shows the cell voltage, just to show you that the power really is going down. You're electrolyzing the decoy away, you're concentrating the solution, the cell voltage is going down. This is a cell that did not produce excess heat, its voltage is also going down. Because we got some temperature excursions, increasing temperatures, going up in temperature, the cell voltage actually falls a little bit. So there's a little bit of departure here. The cell got a little bit hotter. But basically the cell voltage is going down, the power you're putting in is going down, yet the temperature goes up in the cell. And again, these are not big effects. And maybe that's some of the problem in cold fusion. Everybody expected big effects, and a lot of the effects are rather small and easily to miss if you don't observe it carefully. This is just another case. Now this cell is running about 10 degrees hotter, so I have a higher temperature scale here than here. So I get them both on the same graph. This is 10 degrees hotter. But note that this is almost tracking exactly the same slope of the cell that did not produce excess heat for a little while at least, and then it starts to go up again. So this easily shows that it is tracking, the temperature is going down as expected, but then it starts to rise. And you would have expected that to continue, and the temperature should have followed about that line. But instead, it went up quite a ways above that line.
Wait, I don't understand the two scales. What? Is it a degree, cell density, or what?
Yeah, they're just 10-degree difference. Even though, see, these are about the same position here, but for one cell that is 50 degrees, for the other cell that's 60. Because the temperature, otherwise it would be off the chart paper. So I had to adjust I had to do two different scales.
Okay, but the upper scale is the delta T.
Up here, this is just the bath and room temperature. It's a less sensitive, it's a more sensitive scale. It shows the bath temperature doesn't change, and the room temperature is sort of lost in here. This is the room temperature. All this shows is the bath and room temperature.
But the temperature change you're talking about is a degree.
From here to here is it's probably about a degree, roughly about a degree change.
Well, I'm trying to get it.
Right. And
So talking about degree change.
So we're talking about, often we're talking about a degree change in these experiments. But we're measuring temperatures to 100th of a degree. And so a degree change is quite significant. In fact, often the temperature above the bath temperature is at least 10 degrees above the bath temperature. This is even more. Bath is 22, we're up in the 60s, so we're well above that. So you're measuring the temperature changes of over 10 degrees above the bath temperature at an accuracy of 0.01 degrees, so you're measuring of an accuracy of 0.01 per 10 units, or the error would be about 1 in 1,000, the error in the temperature measurement. The error in the calorimetry is about the same as the error in the temperature measurement, which is about 1 part in 1,000. Martin Fleischmann claims you can get even more accurate results than that, but you can measure the calorimetry as accurately as you can measure temperature. This is one final experiment. I won't spend too much time running out of time, but this is the cell that did not produce excess heat, same as before, the temperature is going down. I actually increased the current by about 20 milliamps right here, just as a calibration. It goes up, and then it comes back down, it comes back and follows the same baseline. So you can easily see you can match up those two baselines. Even though you raise the current and temperature went up, it comes back to the same baseline. Well, this other cell is really not even a baseline you can establish. It should have been going down all the time. It goes through an excursion, goes up, you increase the current, it goes up again, but it's way above where it should have been according to that baseline. Now, an interesting factor in these experiments was we saw these transitions in thermistor readings. There's a lot of dots on the chart paper in the cell producing excess heat. What I think this is you're generating high energy photons, maybe X-rays. They hit the thermistor and cause a little excursion. It's not a real temperature, but the thermistor is being bombarded by radiation, electromagnetic radiation, photons, so it jumps up for a minute and comes back down. I later found that by exposing thermistors to a radiation source, I could get similar effects. So there is some source of radiation causing unusual behavior of the thermistor. And one thermistor showed this and the other one did not. Well, the one that did is called, we call thermistor 1. If you go back to the cell design, thermistor 1 is this thermistor right here. Radiation from the palladium cathode can go right through the coils and strike that thermistor without anything interfering with its path. This thermistor that did not show that effect, radiation from the palladium has to go up this way and would hit the palladium, the platinum coil, the other electrode would strike that before it got to the thermistor, plus that thermistor is further away. So it's not. So we got unusual thermistor effects with one where we had a direct radiation path, and the other one we did not in the same cell.
What kind of radiation are you looking at?
I don't really know. I didn't even put this in the paper because it would be controversial. I didn't want to argue directories about it. I would just suggest electromagnetic radiation. Some people have found X-rays. I've seen evidence for film exposure. I've seen high readings on a Geiger counter nearby the cell. So it is just high energy photons such as X-rays, perhaps. That's what I would say, produced by the reaction. This is the plated boron material. This is a product presented in San Francisco in September, a paper, and I'll just have to go through this rather fast. This is an entirely different type of cell in the fact that it is a doer. You have a vacuum here, and this is silver, so the heat transfer is by radiation, not by conduction. The heat is transferred to the bath through a radiation process through the glass doer. In the Fleischmann and Pons original design, this is what I used in Japan. Now you can calculate by the Stefan-Boltzmann law that the transfer of energy by radiations using the Stefan-Boltzmann constant and the radiation area of the cell I used, you can calculate the minimum value of the radiating heat transfer coefficient, which would be 0.75 times 10 to the minus 9 watts per degree to the fourth power, minus fourth power. You probably lose some other heat by conduction, so I would expect that this important constant that you're using in calculating the calorimetry would be somewhere in the neighborhood of 0.8 times 10 to the minus 9 watts per degree to the minus fourth power. Well, Martin Fleischmann's analysis, and he spent a lot part of this report, he actually gets 0.85065 times 10 to the minus 9. Now, whether that's really that significant, he claims it is, but I don't know for sure. But he comes very close to what we calculate. The other important parameter is the heat capacity of the calorimeter itself, which is this figure right here. These are the equations that we use in calorimetry. It would take too much time to go through these. Nobody has ever criticized these equations. They're based on first law of thermodynamics. The power, the change in your calorimetry is the power in, excess electrochemical power, excess power, and the internal heater you turn on and off, and the power that comes out, power P, the gas stream. And this shows what these different terms are, so that would take a little bit of time to go through all that. But nobody has attacked these equations. They're based on first law of thermodynamics. They're in the physical chemistry textbook, and I see nothing wrong with them, and nobody has found any error in these equations. Now, if I just calculate the water equivalent of of the cell. This cell is much larger, almost 90 cubic centimeters. From the heat capacity of heavy water, I can calculate 419 joules per degree is the heat capacity of that cell. So there's also some blast, the water is packed in, and so if you add that on, you can calculate about the same result you got about heat capacity of the system is about 450 joules per degree. And so you can calculate both his parameters theoretically and come out pretty close. This shows an example of positive feedback. This is a palladium-boron electrode that almost always produces excess heat. This is the cell temperature. We turn on an internal heater of 0.25 watts so the temperature rises while that internal heater is on. Then we turn it off again and the temperature goes back down. So that's the scale over here. This is the cell voltage. When the cell heats up, the voltage falls down because the conductivity is better. When the turns the heater off, the cell cools down and the voltage comes back up. This is a very minor effect, but very important. If you have excess power and you have positive feedback, this does not relax back to the same baseline. Because we heated up the cell, we increase the excess power effect. When it comes back down, it's on a different baseline. Now, many other experiments, it comes back to the same baseline when you don't have any excess power effect. But a very small effect you would easily overlook. But you can always spot when the cell is losing excess power. When you heat it up, it does not come back to the same baseline. Very simple test of when you have excess power present. This shows actually Martin Fleischmann's calculation of the excess power during that same time period. This is very early in the experiment. Often these experiments don't produce excess heat until 10 days of electrolysis. So this produces excess heat almost from the start. Not very much, it's only a little bit, maybe 5 millivolts, depending. But when you turn on the heat of the cell up, the excess power goes up. When you turn the cell off and it starts going down, the excess power comes back down. But it doesn't come back down to zero. There's still some excess power there. Not a lot, a few 5 or 10 millivolts. This is another way to show the same thing. We ignore the fact that we have an excess, we have an internal heater in there, and we see if we can recapture that heat put in by the internal heater. So we assume it's not there, and see if we can recapture it. So we have a larger scale here. Before we turn on the internal heater, the excess power is close to zero, a little bit above. When we turn it on, we do get the power of that heater, 0.250 watts. The jump from here to here is very definite, 0.25. So we recapture exactly the heat of the internal heater when we turn it on. But it keeps going up. The cell is getting hotter, the excess power keeps going up. When we finally turn off that internal heater, we again get an exact change of 0.25 watts. From here to here is exactly 0.25 watts. We turn the heater off. But there is excess power that continues. And the cell cools down and gradually decreases. But heating the cell up increases the excess power effect. And this happens many times. The effect becomes larger when you increase the temperature. This just summarizes for the entire experiment of palladium-boron, the excess power. It showed excess heat very early. It had a period here of large excess heat. It had another period here of large excess heat. We had one day here that did not have any excess heat, day 61. That turned out to be useful for calibration. We're kind of glad we have that day to calibrate everything. But it went down to zero here and then back up again. Before I left Japan, I did my own analysis with a lot of approximations, but I only had a few weeks to do the report. And this is what I came up with. I had a different cell constant, a different value here. But I still saw a period here of excess heat and a period here of excess heat and smaller periods in between. And in fact, if you overlap these, you can almost see I get the same peaks that he saw, though it's a different time scale. And I get the same peaks over here, similar to Mark. So completely different analysis. What I did approximately in Japan, what Martin Fleischmann spent months doing later, we were very close agreement on excess power effect on that experiment. We drove the cell to boiling, and the excess power goes up as it boils away. It actually goes up to about 25 watts per cubic centimeter point, the cell boiled dry, and so there was no electrochemical power going in. So no power input, but the excess power still continued. It continued about 3 hours. With no extra power going in, the excess power continued. It gradually decayed away, but it continued for about 3 hours after the cell had boiled dry and no electrochemistry was going on. Well, I'll just finish up real quickly. Because the boiling point of LIOH, how it changes the temperature, that's important in this analysis. Boiling point elevation, this is physical chemistry, you can calculate it. We measured it in the laboratory last semester, and the boiling point elevation for concentrated solutions is greater for KOH than it is for sodium hydroxide. And this was missing in the literature, and it follows the same trend. The boiling point elevation in LIOH is lower than sodium hydroxide, and we're going to continue and look at that in heavy water as the next step. The possible role of the boron, it makes the plating much harder. The deuterium comes out much slower. The boron sits in the grain boundaries and retards the deuterium getting back out. But this is a key process, I think. Every sample that has worked well has been oxygen-free. It's been made in a way that you eliminate oxygen. When you arc melt this, the boron combines with oxygen, is skimmed to the surface according to Dr. Iman, who made it, and is skimmed off to the plating. So boron is an oxygen getter. And so when you add boron to the plating, you combine the oxygen out of it, and the plating is fairly oxygen-free. So I think that's the key, material key to this whole problem is you have to make plating in such a way that there's no oxygen present, or very little. The sample that Fleischmann and Pons used initially was made under cracked ammonia. Well, cracked ammonia is hydrogen. The hydrogen combines with the oxygen. Then Johnson Matthey couldn't make it that way, and nothing worked. So after they made the announcement, they found they couldn't get the effect themselves for a long time because they had plating made in a different manner. It has to be oxygen-free for some reason. A summary of, you see it appears early, we have positive feedback, the effect increases when the temperature goes up. We did get a total of 1.05 megajoules of excess enthalpy. You cannot explain that by a chemical process, that much excess enthalpy. The cell boil-off produced the largest excess power effect, and this material is fairly reproducible. 8 out of 9 experiments using platinum boron give excess enthalpy. In summary, 12 years of co-fusion research. Helium 4 is the main product. The excess enthalpy requires a high degree of loading. The effects are often small. You got to be prepared to look for 1 watt per cubic centimeter if you're going to work in this area. Platinum boron materials give the best reproducibility. The effect increases with the temperature. Research is continuing in Italy and other countries. Italy has a government-funded program, in fact. I think the scientific method has failed in this area because ridicule was taken over rather than scientific discussions. Various theories, a lot of different theories of QED, and it'll be the 9th International Conference in China. And I just want to finish up with a couple of quick things. The letter to the CNE News is December 24th. Spock and Pan Voss wrote this letter in CNN News in December 24th. We believe the situation will not change until editorial policies of majority of scientific journals which currently do not allow co-fusion papers to be even reviewed. They're just sent back. They will not even send them out for review. A personal experience, I sent a paper in December. They said they were going to review it, Journal of Electrochemical Society. I gave this letter back in January from the editor, this went all the way to the editor. After they said they were going to send it out for review, he says, therefore we will return your manuscript to you without having to review it. So that's what happens when you submit a paper in this topic. You send it to a journal, they send it back. It never gets reviewed. And on a more encouraging note, this was faxed to me last Friday. The U.S. Army Space and Missile Defense Command called for grant announcements. And in this grant announcement, I was quite surprised and pleased to see under potential research areas of knowledge, energy power sources include cold fusion topics, where you can submit a grant for funding from U.S. Space and Missile Defense Command It's kind of unusual. You have a government agency that who's willing to fund it, but you don't have journals willing to publish their results. So that's what they stand today. Okay, thank you.
All judgment was give up the room without having questions and discussions. However, Dr. Miles going immediately to the James Union building, we'll have lunch in the faculty dining room. That'll be an excellent place to continue these discussions. Also know there's a lot of visitors here, Dr. Achievement and other guests. We can do our seminars weekly, we're always welcome to come. However, next week would be a bad time to come here because we're actually going to Keithley University Center for the chemistry folks demo menu will be our seminar for that week. Dr. White, is that time still 9:15 to 11?
9:30 to
9:30 to 11. Maybe good thing to do to come and watch chemistry program. Until then, let's thank Dr. Miles for